All right, welcome back. We did a little bit of this the other day, or in the other video on graphing, but now we're going to take an even more in-depth look at just different types of graphs that you might see. There's obviously an infinite number of graphs that you could see, and just given a certain type of graph, predicting what the other two types of graphs would be. So the graphs, again, are position versus time graphs, velocity versus time, and acceleration versus time. Based on what we're given, we're going to figure out what the others should look like. This shouldn't be a guessing game. There are methods that you use in order to do this. Really, what you need to think about is the slope, okay, and how the slope of any graph relates to the other types of graphs, and the area under the curve. Those are the two big things that you want to think of. So, what we have here to start off is a position versus time graph. We see, and we can run through those questions that we always ask ourselves as well. We see that the position is always positive. We see that it's increasing, meaning that the slope is also positive, and we also see that the slope itself is increasing. Okay? Remember, this is one of our facts that we know for a position versus time graph. The slope of a position versus time graph tells us the velocity. We see that the slope is very low down here, not very steep, and gets steeper as we go. What that should tell us is that the velocity starts very low and gets bigger as we go, because the slope of an x versus t graph is the velocity. So a low slope in the beginning going up to a higher slope by the end should be a low velocity transforming into a high velocity. That might look something like this. We're going to assume here that there's constant acceleration. So basically what that means is our graphs for velocity shouldn't have curves in them. This should be straight line segments, maybe straight line segments of different slopes, but straight line segments nonetheless, nothing like this. So this is what the velocity graph would look like, okay? Something sort of like that. Now also remember that the slope of a velocity versus time graph should tell us the acceleration. We see that the velocity is always positive here. That makes sense because the slope of this graph was always positive. We also see that the slope is constant. The slope is the slope itself is positive, and we know that so it's positive and it's constant. We know that the slope of a velocity versus time graph tells us the acceleration. So therefore, since the slope is positive and constant for this velocity versus time graph, my acceleration versus time graph should show acceleration being positive and constant. Something more or less like this. Okay, and there you go. And again, these three graphs all show the same motion, just different aspects of that motion. Okay, one graph shows how the position changes, one graph shows how the velocity changes, the other graph shows the acceleration. But they all show the same sort of thing, or they all trace back to the same root motion. What sort of motion would this be? I would say that this is just an object that is accelerating from rest. Starts at rest and then it accelerates. Okay, simple as that. This next one, we're given the velocity graph and we're supposed to determine both the position versus time and the acceleration versus time graphs. Now, I think it's much easier to go from left to right. So what we're going to do first is we're going to fill in the acceleration part of this. Then we'll go back and figure out what the position versus time graph is supposed to look like. Looking at this graph, we see that the velocity is always positive. However, the velocity is decreasing, meaning the slope is negative, but that slope is constant. So that's the key parts. The slope here is negative but constant. Slope of a velocity versus time graph is acceleration. So since the slope is negative and constant, the acceleration must be negative and constant. Looks something like this. Okay, there we go, nice and easy. Now, going back to the x versus t graph, there's a couple different ways you can think about this. Remember that velocity is the slope of a position versus time graph. And we just said that the velocity it starts off very high and becomes 0 at the end. And it also says to assume x naught is 0. So we know that the initial position is there. If we were showing since the velocity is very high in the beginning and goes towards 0 at the end, then that means that the slope of this graph should be very high in the beginning and goes towards 0 at the end. We also know, since the area under the curve for a velocity versus time graph is the displacement, or in other words, the change in position, we know that since this area would be positive, since it's above the x-axis, the position should increase. And that makes sense because we're going to have a very positive slope to start off because of very positive velocity, and it's going to end up being 0. It'll look something like this. Very positive slope, but that slope is decreasing as the velocity decreases to something that approaches 0, like that. Okay? What's happening in this motion, in these 3 graphs? The object was moving forward quickly, but then it slowed to a stop. It's kind of like the second half of the motion for this. You have an object accelerating from rest, and then it slows to a stop, okay? These are completely separate motions all on their own, but imagine if you combine them, it's kind of like one of the examples that we talked about in the last video. Okay, now we've got kind of the inverse of that. We have an object, let's see. The position is always positive, but we notice that the position is decreasing. In other words, the slope is negative this whole time, and the slope is changing. So interestingly here, we have a changing slope. It starts off very negative and becomes less negative as we go. So that tells us the velocity. Since this is a position versus time graph, the slope is the velocity. The velocity should start off very negative and become less negative as we go. To me, that seems like something that should be about like this. There's something there's a picture of it for an object that starts off, the velocity starts off negative, but becomes closer and closer to positive. Now that seems a little weird, just because the graph is down here, but notice that the velocity is negative the entire time because this is always a negative slope. It's a downward trending slope, okay? The position is decreasing. In other words, it's moving backwards. Negative velocity just means an object happens to be moving backwards or in the direction opposite that which was called positive. To look at the acceleration, okay? Let's see. Slope of velocity versus time graph is the acceleration. This slope is positive. It's an upward trending velocity. Don't pay attention to the fact that it's negative velocity. It is an upward trend, so that's a positive slope, and it's a constant positive slope. So that acceleration is going to be positive. It actually looks like this. I want to make one point right here since we've dealt with a whole bunch of different types of acceleration graphs like this, okay? Notice that when we had a positive velocity and a positive acceleration, we ended up with an object that, well, this says accelerated from rest, but look at this object. It's very clearly speeding up, okay? It's moving forward because it's positive velocity, and it's also got positive acceleration, so it's moving forward at a faster and faster rate. It is speeding up. It's going faster and faster. The faster something is moving, the closer the slope is to being infinite. On the other hand, here we have a positive velocity, because the velocity is always above the x-axis, but a negative acceleration. Look what happens to this object. It slows to a stop. Okay? Positive velocity, positive acceleration, speeding up. Positive velocity, negative acceleration, slowing down. Down here we have negative velocity because it's below the x-axis, but positive acceleration, this object is also slowing down. This object would be like if you have a car that's in reverse. You're moving in a car in reverse, but that car is slowing down to a stop. Okay? So interestingly, when the velocity and the acceleration, remember this is negative, this is positive, when they do not have the same sign, when one is positive and one is negative, the object must be slowing down. When the object and the velocity, when the object has the same sign for both the velocity and acceleration, that object is speeding up. Matter of fact, I don't think I have the example on here. Oh, I will have the example on here. Okay, let's get to the next one. Okay, then we'll kind of bring this point full circle. We've got a weird graph going on here. We have velocity. Let's see, it starts off negative, it gets more and more negative, then it jumps up really quick. Now it's positive, but then the positive velocity decreases back to 0. So velocity starts at 0, it goes down, it jumps way up to be positive, and then it goes down again. Again, I'm going to go to the right first here, okay? Since the slope of velocity versus time indicates the acceleration, this is a negative slope. It's a downward trending velocity, and it's constant. So that implies a negative constant acceleration for just about half. So that's going to look like this. Okay. Then we have a very, very, very steep upward slope. It seems about constant. That means a really, really high acceleration for that tiny little bit of time. So I'm going to draw that like this. Okay, I'm going to draw it basically like a discontinuity. For this tiny little bit of time, there's a huge, very positive acceleration. And then we're back to, actually, if you look at this, it's pretty much the same slope. It's a negative slope, but it's constant. So I'm actually going to draw this back down like this. That's your acceleration graph. You have a fairly constant acceleration except for that spike in the middle. Now, how do we figure out what the motion itself looks like? It says assume x naught is positive, so we're just going to put this up here. We have a velocity that starts at 0. Because we have a velocity that starts at 0, that tells me that the slope over here should start at approximately 0. But that velocity decreases. The velocity gets more negative, meaning the slope should get more negative, meaning we have a downward trend in our position. That might look something like this. Then we have a very, very, okay, and then the velocity changes from being negative to positive almost instantaneously. So instead of having something that's going down, we almost have the exact same thing going up, and then we have a positive velocity, but then it decreases back to 0. So I'm going to transition from a big negative velocity to basically the same velocity, let me take a step back. We have a very negative velocity here, meaning a very negative slope. We have a very positive velocity here, meaning we need a positive slope, about the same steepness. So maybe something like this, and then that slope is going to change until it gets back to 0. So something that looks approximately like this. Okay. Now, what would this motion be? I think that this motion could be an object that is dropped and then bounces back up. I apologize, I'm not showing enough of that. And then bounces back up. Okay, and let me illustrate my last point here. Notice that when the velocity was negative and the acceleration was negative, this was the object. If this is the bounce part of the object, this is when it's speeding up. It's going faster and faster as it goes towards the ground. Then we have this big change. But then look up here. We still have a negative acceleration during the second half of the motion, but we have a positive velocity. As the object rebounds off the ground and goes up, what's it doing? It's slowing down. So again, this just illustrates the point that just because you have a negative velocity, that does not mean that the object is slowing down. Matter of fact, I'll write out a couple of rules here, and these are very, very important. You should write them out as well. When the velocity and the acceleration have the same sign, positive or negative, an object will speed up. If they have different signs, the object slows down. That is a really helpful tool, and we can practice that a lot in class until we get it. That's a really helpful tool for understanding what the velocity and the sign of the velocity, the sign of the acceleration, because it's usually pretty easy to tell if the velocity is positive or negative. Okay, is the object moving forward? Is it moving backwards? Is it moving towards the or depending on where it is it moving towards the positive infinity? Is it moving towards negative infinity? It's a lot harder to tell sometimes whether the acceleration is positive or negative, and this sometimes can help. Okay, if an object's speeding up and you know the sign of one of the velocity or acceleration, you know the sign of the other. If it's slowing down and you know the sign of one, you also know the sign of the other. A few more examples. This next one is pretty straightforward. Let's see. Okay, there we go. Okay, next one's pretty straightforward. We're given the velocity we're going to move to the right first. This velocity is, let's see, negative. This object's moving backwards, therefore, and constant. The velocity is constant. That means that the slope of the velocity versus time graph, you can tell that it's 0. Okay, the slope is 0. That means the acceleration must be 0. Like that. And as far as position goes, a couple different ways we could think about this. We know the velocity itself is constant and negative. That must mean that the slope of the position versus time graph is constant and negative. If we're starting x naught at 0, a constant negative slope means that we have to go down from there. Like so. Well, that's about as constant as I can make it. There we go. Another way to think about this is the area here would be negative since the best fit line is below the x-axis. So since the area is negative, the object must be moving backwards, like so. What would this be like? This is like walking backwards. At a constant velocity. Okay. Next one. We have a position versus time graph. We see that the position is always positive. We see that the position goes up, kind of levels off, and then comes back down, which means the slope is positive, then 0, and then negative, which should tell us something about the velocity. And, well, actually, let's just go right to the velocity. If the slope, remember the slope of position versus time is the velocity. The slope starts off very positive, levels off to 0, and then becomes negative. That tells me that the velocity starts off positive. When it levels off here, when the slope is 0, the velocity should be 0, and then at the end, the velocity is very negative. That actually should look approximately like this. Just about like that. Okay? And then finally, for the acceleration, we know that there is acceleration here because the slope is changing, but it's easier to look at just the velocity versus time graph. We see that the slope is negative. It's a downward trend for the velocity the entire time. The slope is negative and constant. Slope of velocity versus time is acceleration. Since the slope is negative and constant, the acceleration should be negative and constant. This is actually a very important graph. It's a graph of an object that gets thrown up and then just falls back toward the ground. It's not a graph for while you're throwing it, while the object's in your hand. It's a graph for after the object has left your hand and it's just moving through the atmosphere, through the air. Okay? The only thing really affecting that object right there is gravity. We'll talk more about that in some future videos. So this is throwing an object upward and then letting it come back down. Good. These next two examples are a little bit more complicated, but it's not uncommon to see things like this. Matter of fact, this one is just the reverse of one that we've already done, and this is actually a graph that if we get to the lab this year, if we do the elevator lab, you will see this. Okay, so this one, we see that we have acceleration graphs this time. We're told in both of them that the initial velocity is 0, so I'm just going to mark that down right now. And we're told that the initial x position for this one is positive, so I'm going to mark that down. And over here, we're told the initial position is 0. So I'll just mark that down so I don't forget. We see that we have a negative acceleration followed by an immediate positive acceleration. It looks like the accelerations are about the same. We remember that acceleration is the slope of a velocity versus time graph. So if we have a negative but constant acceleration here, that means we should have a negative but constant slope for the first half on our velocity versus time graph. That might look something like this. Then we have a positive but constant acceleration. So we should have a positive but constant slope for our velocity versus time graph, going from where we left off. And notice that since the areas are about the same, remember the area under an acceleration versus time graph tells us change in velocity. We lose some velocity in this section, but we gain it right back here. And since those areas are equal, there should be ultimately no change in velocity, which means we should end up right where we left off at 0 velocity. Remember also that the velocity versus time graph, or well, velocity in general, is the slope of the position versus time graph. Since this velocity decreases at a constant rate, okay, the velocity is negative and it becomes more negative. That means, it starts at 0 and becomes more negative. That tells me that the slope of the position versus time graph should start at 0 and become more negative for the first half. So something maybe like that. Then the velocity becomes more positive until it gets back to 0. That should look approximately like that. Okay? So we see that this object starts off above in front of the origin, we should say, and it has a negative velocity the entire time, shown by this negative slope. It speeds up, it goes towards the origin, but then it starts to slow down and stops approximately when it gets back to the origin. And again, notice, negative velocity, even though there's a positive slope, don't get tricked. This is negative velocity because it's below the x-axis, positive acceleration, object is slowing down during the second half. During the first half, when the velocity and the acceleration were both negative, that was during the first part when the object was actually speeding up because the slope is getting steeper and steeper. The last one is going to be very similar. We start off with a lot of positive acceleration. Remember, acceleration is the slope of v versus t. Since this is a constant positive acceleration, we must have a constant positive slope in the first third of our v versus t graph. I'm going to draw that like this. Then we have no acceleration. If there's no acceleration, that indicates that, well, there's no acceleration, the velocity shouldn't change. So for this middle third, our velocity should stay the same. And then, for the last third of our graph, we have a negative acceleration, a negative constant acceleration. That means that our slope of our v versus t graph should be negative and constant. And again, since the area under the curve represents change in velocity, these areas under the curve are about the same size. We should lose all of that velocity that we gained. The velocity ends up back at 0. Finally, our position versus time. Oh, I didn't even describe the motion here. Let me go back to that for just a second. For this last one, what's the motion? Here's what I came up with. You have an object that accelerates backward from rest. And then it brakes to a stop. So imagine you're like, I don't know, like backing out of your driveway. You start the car, you start to accelerate backwards, you're moving backwards faster and faster, but then you are getting ready to turn, you're pulling out into the road, so you have to put on your brakes. So then you put on the brakes, you have a positive acceleration now, but you're still moving backwards, so you come to a stop, and then you finally come to a stop. And then if this graph were to continue, the rest of it is just your drive forward after that. Anyways, back to this last example. Remember, we have positive velocity this entire time, so that means the position should be increasing pretty much the entire time. And that is also borne out by the area under a velocity versus time graph, or in this case, above, between the graph itself and the x-axis. That means that it should be gaining position. We have a velocity that is increasing during the first third, which means we should have a slope on our position versus time graph that is increasing. Maybe something that looks about like that. Then we have a section where the velocity is positive, but constant, which means our slope for x versus t should be positive and constant, such as like this. Notice that the slope isn't changing anymore during that section. It's fairly constant. before it was changing. And then we have a positive, it's still positive velocity, but it's going down, it's decreasing, okay? So positive velocity, but it's getting closer and closer to zero, means we should have a positive slope on our x versus t graph that's getting closer and closer to zero. Something like that or so. Now, this graph is actually a perfect graph for someone who is riding an elevator upward. It shows that because if you get in an elevator, let's say on the ground floor, and you're taking it up, at first you're motionless, okay? You have no velocity right at the beginning. You're at the ground floor. In order to start moving, you have to accelerate upwards, okay? So as you accelerate upwards, you pick up some speed. In the middle of the trip, there's no acceleration. You're moving at a constant speed. And then at the end, in order to stop, if you're moving up and you want to slow down, you need to accelerate downwards, which would be negative in this case. That's where this negative acceleration comes in here. So our velocity decreases, and we have this curve off that shows us kind of topping off at the peak, at the highest point of your elevator ride. Okay? Hopefully, you've got a little bit more practice now with reading graphs and predicting what other graphs might look like based on some given graphs. Again, we'll be doing labs on this. We'll be practicing this in class. This is something that is an acquired skill, but it is really important. And if you can do this, then you have a very good grasp of this kinematics unit. You can do pretty much anything that we ask of you concerning graphs. Always remember to analyze graphs using the 3 questions that we learned about, and always remember, perhaps, we'll probably have spent some time at this point by writing them down and kind of testing you on them, but always remember those 10 or so different facts about graphs, about position, velocity, and acceleration graphs. You should have those memorized at this point, okay? If you have any questions, let me know. Otherwise, next time I see you, we will be talking about vectors. See you later.